Hello again. So we're going to start with section 1.5 now, solution sets of linear systems. Okay. So before we really dive into solution sets, we want to ground this first with a definition. So we're going to talk about a homogeneous system. Okay. Homogeneous systems have the form AX equals 0. Okay. So homogeneous system can be written as AX equals 0. So again, here X is a vector, A is a matrix, and 0 is the 0 vector. Okay? So where A is an M by N matrix, and 0 is the 0 vector in R. Okay, and I want you to think here, is it Rm or Rn? Right, so remember that we're going to multiply a matrix A that has M rows and N columns. We're multiplying it by some vector X here. Okay, so we're going across the rows and down the vector X. Okay, so each one will have a row times a column, a row times a column, and a row times a column. So we do that, the number of rows that there are. Okay, so this is the 0 vector in Rm. Okay, Rm, the number of rows that our matrix has. Okay. All right, so let's flesh this out with a little more specificity. So we're looking at homogeneous systems. They're AX equals 0. Okay. Now the nice thing we know about 0 is that in order to multiply and get 0, one of my factors has to be 0. We know that just from algebra, right? We use that all the time, the 0 factor property. You should have used that in calculus, algebra, anywhere along the way. Okay. So we know that this has to multiply to be 0. Well, if it's a 0 matrix, that's just boring altogether. Okay, so we don't want to think of A as a 0 matrix. Well, that would mean that if X is 0, that's certainly a solution. Okay, so if I have a homogeneous system, AX equals 0, I know that if X is equal to 0 is a solution. Okay, doesn't matter what the AX equals 0 is. It doesn't matter what your A is, right? If I know if I multiply it by 0, I'm going to get 0 out. Okay? So that is a solution. We call this the trivial solution. So the trivial solution is when X in AX equals 0 is 0. Okay? So we always have that trivial solution. It doesn't matter what A is, I always have a trivial solution. Okay? Anytime that sets up. Okay? So then what we want to mainly look at then, what we're really interested in is non-trivial solutions. Okay? So let's consider a couple of different matrices here. So let's take the matrix 1, 2, 3, negative 1, 1, 0, and 2, 4, 1. So there's my matrix A. I'm going to multiply that times a vector x, x1, x2, x3. We'll set that equal to the 0 vector. So I have a homogeneous system. Okay, so one situation is definitely going to be if x1 is equal to x2 is equal to x3, that's definitely 0. That's definitely a solution. Okay, so our question is, are there other solutions? Okay, well, given what we know from our previous sections that we can set this up as an augmented matrix. So 1, 2, 3, and then 2, 4, 1 on the bottom row. And we're going to augment that, sorry, drew a bar there, with our vector on the right-hand side, right? We can take this matrix equation, make it equivalent to an augmented matrix. Then we're going to row reduce that matrix. Again, just a refresher on quick row reduction if you're not doing the hard method here. So I got a 3x4 matrix. Sorry, let me get that out of the glare for you. So I got a 3x4 matrix. Going to type my matrix in here, 1, 2, 3 going across. Okay, then I've got 0 for the fourth spot. Then negative 1, 1. No, sorry, that messed up there. So let's try this 1, 2, 3. We've got that taken care of. Second row, I've got negative 1, 1, 0, and 0. See what the problem is. Got my dimensions wrong. There we go. So now I've got 1, 2, 3, 0 on the top row. Second row, I've got negative 1, 0, 0. Then bottom row, 2, 4, 1, and 0. Okay, so now I am ready to do a RREF. So I go back to my home screen, I go over to math. Oh, not REF, sorry about that. Go up to RREF, and then matrix A. And we see that I get a nice clean system there. 1's all along the diagonal and 0's elsewhere. So that reduces to 1, 1, 1 with 0's there for the rest of it. Okay, so each variable is 0. So that is the only solution. Okay, that's the only solution to this system. There's nothing else over here. Okay, so not every system has a non-trivial solution. In fact, a great many of them do not. Okay, so let's go to another one here. I'm going to have 1, negative 1, 2. I'm going to use that same first row. 2, 2, 2 in the second. And we'll make this one 3, 1, and 4. Okay, so I can multiply that by x1, x2, x3. And again, we want to set that equal to the 0 vector. Okay. All right, so let's, again, row reduce that matrix. So type in your matrix here, 1, 2, 3, 0 on the first row, negative 1, 2, 1, 0 on the second row, 2, 2, 4, and 0 on the third row. And we're going to row reduce that. And so when I row reduce that, I get the following augmented matrix here. So I get 1, 0, 1, 0, 0, 1, 1, 0, and 0's all along the bottom row. Okay, so now I have a situation where I have a free variable, right? So x3 is a free variable. So whenever I have a free variable, that's going to give me some possible non-trivial solutions. Okay, now we know from our previous sections that we can write the solution to this, right? We talked about writing solutions. This is going to be x1 plus x3 equals 0. I'm going to go through the steps here just to make sure we reinforce it. Second row there is x2 plus x3 is equal to 0. And then the last row I have that x3 is 3. Okay, and we could write that as x3 equals x3 just as well. Those would be equivalent expressions. Okay, and so then what we said is I get each one with a single variable by itself. So I have x1 is equal to negative x3. x2 is also equal to negative x3. And then x3 is just x3. Okay, so I can pick any value now for x3, and that will give me a solution. So for example, if I pick x3 to be 1, well then negative x3 is negative 1. So negative 1, negative 1, 1 is a solution. Okay, so if I go back to my matrix, so this is my solution candidate here. I go back to my matrix I started with here. So I've got 1, 2, 3, negative 1, 2, 1, and 2, 2, 4. And we're multiplying that by this solution candidate we just found, negative 1, and 1. Okay, and so remember, we go across the row and down the column vector. So negative 1 times 1 is negative 1. Negative 1 times 2 is negative 2, so that's negative 3 so far. And 1 times 3 is 3, so I got 0. 3 minus 3 is 0. Second row, negative 1 times negative 1 is a positive 1. Negative 1 times 2 is a negative 2, and then 1 times 1 is a positive 2, so positive 2 and negative 2 gets me 0. And then the same thing here, negative 2, and a positive 4 all go together to make 0, okay? But that is certainly not the only solution, okay? I could pick any value for x3 and get another one. So say make x3 2. Well, then the other coordinates would be negative 2 and negative 2. You'll make x3 3 halves. Then you get negative 3 halves and negative 3 halves, okay? So ultimately what we have is we're multiplying by something. So this really is this vector times whatever x3 value you choose. So if I pick 1, I just get the vector by itself. If I pick 2, I multiply everybody by 2. If I pick 3, I multiply everybody by 3, so forth. Okay? So you only have non-trivial solutions if you have a free variable. Okay? So non-trivial solutions occur only if there is a free variable. Non-trivial solutions occur only if there's a free variable. Okay, and a free variable occurs only if one of your vectors is a multiple of the other vectors. Okay, so remember what we had in the previous section. We talked about how if I only have a multiple for the second vector, then I don't get any new dimensions. You know, I just still have a line instead of getting all of the R2 plane or all of the of a plane in R3. Okay, so that third vector here, notice this third vector is actually a combination of the first two. 1 plus 2 gets me 3. Negative 1 plus 2 is 1. And then 2 plus 2 is 4. Okay, so non-trivial solutions only occur if there's a free variable. They only occur if one of the vectors is a linear combination of the others. Okay, so notice this system here had a free variable. That means that this third vector is a linear combination. Okay, so for example, I could write this as A1, A2, and A3, and notice that A1 plus A2 is equal to A3. So that is a linear combination. So you see how linear combinations from the last section fit into this talk of homogeneous systems and solution sets. Okay, let's go to another example. I'll make sure I write down a good example for you. Don't want to write down the wrong things. I've done a couple of times. Okay, so I'm going to have my system here. 1, 2, 1, 2, and we'll augment that with 0. Okay, so I have my two vectors here. Notice these two vectors are identical. Okay, so this matrix then would row reduce to 1, 1, 0, 0, 0, 0. Right? You can think about what that row operation is. It's negative 2 times row 1 plus row 2 replaces row 2. Okay, so it's pretty easy to write the solution set here. This is going to be x1 plus x2 is equal to 0, and then x2 is free, which means I could write that x1 is equal to negative x2, and again, x2 is free. So I could write my solution set then as a vector. Negative 1, 1, again, that's the coefficients here on these, times my free variable x2. Okay, and we could write that in parametric form, right? Instead of using x2, I could use t or s, so it's easy to write those in parametric form. Okay, so that's a pretty straightforward one. Let's go to another one here. So say I have 3x1 plus 5x2 minus 4x3 is equal to 0. Then I have negative 3x1 minus 2x2 plus 4x3 is equal to 0. Then I have 6x1 plus x2 minus 8x3 is equal to 0. There's my system. Okay, so this is a homogeneous system because all of these are equal over here. Okay, so I can actually just look at the coefficient matrix, right? Notice that whenever I do row operations on that column of all zeros, I still get all zeros. Okay, so if you don't want to write down that fourth column of all zeros, you don't really have to. It's not a requirement because we ultimately have a homogeneous system. Those zeros are going to stay zeros. Okay. All right, so again, I want to make sure we're getting lots of practice here on using the calculator because it's going to be a beneficial tool for you. You can also go to rrefcalculator.com is another useful site, and you can use Wolfram Alpha as well to do matrices. The syntax is a little tricky in Wolfram Alpha, so rrefcalculator.com is useful. But again, I'm typing in my matrix here. Okay, 6, 1, negative 8 on the bottom row. And then we're going to row reduce that. Okay, so you see I've got 1, 0, and then a negative 1.333. So that is a negative 4/3. Okay, so 1, 0, negative 4/3, 0, 1, 0, 0, 0, 0. And then I'm going to get all zeros in that last column again. I also want to make a point here to show you, you can use the fraction command. A lot of you may be familiar with that. You can do math, enter, and make it a fraction. You can actually do that with matrices as well. You see it changed my fraction there to a -4/3. Okay, so now I can write the solution set for this system. Well, this system has a solution set where x1 is equal to 4/3 x3. x2 is actually just equal to 0, right? x2 equals 0. And then x3, I don't have a pivot in that third column, so x3 is free. So my column vector, my solution is a vector then, would be 4/3, 0, 1 times the vector x3, or perhaps we used a parametric equation, parametric representation, and we used t instead of x3. Okay? Now we want to make some observations comparing this homogeneous system to a non-homogeneous system. Okay? So I'm going to take the same system, try to use a different color here. I'm going to take the same system, and instead of using 0, 0, 0, I'm going to use 1, 1, 1 for my vector here. Okay, I'm going to use all ones. Okay, so now I'm going to have a matrix. It's going to be 3, 5, -4, -3, -2, 4, just as before, 6, 1, -8. But now it's augmented with these ones. Okay, we're going to row reduce that. Okay, feel free to use row operations. Happy to talk with you about row operations some more if you need to, but I'm going to use a calculator just in the interest of expediency. So I got that same matrix I just had before, so use that in your calculator input. Just change those to ones, and then we'll come back here and we will row reduce that. Okay, and we get an interesting, I hit the wrong button. Let me try that again. We still get an interesting result. That part I meant, but I hit the wrong button there. Okay, and so we notice here I've got that same form: 1, 0, -1.33, 0, 1, 0, 0, 0, 0. Notice on the end here now I've got 0, 0, 1, 0, 0, 1. Okay, so what that means is, let me get that written down, 0, 1, 0, and then I got 0, 0, 0, 1. Remember that if that means I have a pivot in the far right column, if I have a pivot in the far right column, then it has no solution. No solution, okay? So that's certainly a possible result if you have a non-homogeneous system. That is not possible for a homogeneous. So when I had those zeros here, it's got to have a solution. At the very least, it has the trivial solution. Okay, but if I don't have a homogeneous system, I have a non-homogeneous system, I can have no solution as well. Okay, so let's try a different point here. So instead of doing 1, 1, 1, now I'm going to do 8, -5, and 7 for my vector. 8, -5, 7. Okay, so we did 0, 0, 0 for the vector. We did 0 vector. We did 1, 1, 1. Now we're going to do 8, -5, 7. So -3, -2, 4 again, same matrix. 6, 1, -8. But now we're putting that with 8, -5, 7. Okay. 8, -5, 7. Again, I'm going to row reduce this. Okay. Now when we row reduce this, we're doing the same row operations each time. I would add that row to that row, right? My row operations would depend on these numbers here. And so since they're not changing, I'm going to continue to get that same result here in the main part of the matrix. Okay. Where it's going to change is over in the right-hand side. So I'm going to edit my matrix. Okay. I'm going to put 8, -5, 7 here in the last column instead of 1, 1, 1. Instead of 0, 0, 0. And I'm going to do a reduced row echelon form of that. I get that same form on the left, but then I get 1, 1, 0 for the final column. Okay. So I can write a solution set for this. Now I don't have a pivot in the far right, so I'm good there. So this is going to be x1 is equal to 4/3 x3 plus 1. x2 is still equal, x2 now is equal to 1, and x3 is still a free variable. It's still x3. So I can write these as vectors again. This is x3 times 4/3, 0, and 1. Notice that's the same vector we got before, right? I got 4/3, 0, and 1. We got the same vector there, but now I have some tack on here. I have 1, 1, and 0. Okay? So what we notice is in the corresponding non-homogeneous system, the solution sets relate to each other, okay? So my solution set here was a single vector. It was the span of that vector, okay? So let's call it V. Well, we know the span of that vector is a line through the origin. Okay, check back with the last couple of sections. If you're not sure on that, the span of a single vector is going to make a line through the origin. Where now I've got this vector, but then I've added something to it. So just like in algebra or pre-calculus, it's a transformation, it's a shift. Okay, so the non-homogeneous solution is a line parallel to the homogeneous solution. Okay, the homogeneous solution went through the origin. The non-homogeneous is not going to go through the origin, but it is going to be parallel to that line that did go through the origin. That was the span of that single vector V. Okay. So let's look at another one here of the same type and get the feel for relating homogeneous and non-homogeneous solutions. I'm going to have a matrix here. This matrix is 2, 4, negative 6, 4, 8, negative 10, augmented with 0 and 0. So I have two equations, but I have three variables, three columns, right? Okay, so let's do a row operation here. I can take negative 2 copies of row 1 and add them to row 2, because that's going to give me negative 4 here and 4 there. Okay, so I've got 2, 4, negative 6. Row 1 doesn't change. Row 2 now, this is going to be 0. 2, negative 4 and 4 makes 0. Negative 8 and 8 also makes 0. This is going to be a positive 12 and a negative 10, so that's going to make 2. A 0 here. Okay, now all of these are even numbers, so I'm actually going to scale both rows. I'm going to take row 1 and divide it by 2. I'm also going to take row 2 and divide it by 2. And so that gives me a matrix here that's going to then be 1, 2, negative 3, 0, and 0, 0, 1, and 0. Now, I'm not in reduced row echelon form, right, because I have a pivot here and I need a 0 above it. So I need 3 copies of row 2 to cancel the negative 3 in row 1, add that to row 1, and replace row 1. Okay, and so my concluding matrix then is going to be 1, 2, 0, 0, and 0, 0, 1, 0. Okay, 1, 2, 0, 0, and 0, 0, 1, 0. Okay, now I could write a solution set, right? x1 is equal to negative 2x2. So remember, we got to move that to the other side. x2 is free because there is no pivot in that column. And x3 must equal 0. Okay, remember this is augmented. Okay, so that's where your equal sign is. So then as a vector, I could write that solution as negative 2, 1, and 0 with x2. Okay. Now, if I change my system, instead of being homogeneous, I'm going to make it non-homogeneous now. So I'm going to start out with 2, 4, negative 6, and 0. But now I'm going to do 4, 8, negative 10, and 4 on the bottom row. Okay, when you row reduce that, you should get the same numbers here, 0, 0, 1 on the bottom row, but then your right-hand row is going to be 6 and 2. Okay, so your row reduction, your solution set then is going to be negative 2x2 plus 6. x2 is still a free variable, but x3 now is actually equal to 2. So notice again, I have x2 in both of these, so I'm going to get the same vector, negative 2, 1, 0. Right? Notice that's the same vector I got before when it was the homogeneous. But now I have a vector tacked on the end of it that is 6, 0, and 2. So notice it's 0 for x2 because I don't have anything added on out here. 2 then for x3. Okay? So my solution set is a line through the origin. It's the span of this vector. Where my solution set for the non-homogeneous is the span of this vector shifted upward. Okay? So we make that shift then to go to non-homogeneous systems. Okay, so homogeneous systems are really nice to work with because you get all those zeros, so it makes that fairly straightforward to deal with. Okay, your solution sets then make lines. Okay, perhaps you have a multidimensional set though. So let's look at one of that type. Okay, say I take a slightly larger matrix. We'll do a lot of the row reduction ahead of time to make it easier for us to deal with. But we'll take a slightly larger matrix to work with here in our next example. Okay, so this is a big matrix, just so you're prepared. So I've got 1, -4, -2, 0, 3, and -5. Okay. Second row then is going to be 0, 0, 1, 0, 0, -1. Third row is going to be start with 0, 0, 0, 0, so 4 copies of 0 to start with, and then 1, -4. And then my last row is going to be all zeros. Okay, so that's my matrix A. I'm going to multiply that by a vector x. Now this vector x should have the same number of entries as I do columns. So this vector x is going to have 6 components, x1 through x6. And then we are setting that equal to the 0 vector. And I won't write out the 0 vector, I'll just bold it because it's going to be a homogeneous system. Okay, we're looking at ax equals 0. Okay, so let's look at this matrix. This matrix is almost in reduced row echelon form. I have a pivot here, zeros below it, that's good. I have a pivot here, but I don't have a 0 above it. I have a pivot here, I got zeros below, but not quite above, and then this is not a pivot column, so it's okay. Okay, so we want to take this pivot column here and do some row operations. Okay, I want to get a 0 above it. So I'm going to need -3 copies of row 3, add that to row 1, and replace row 1 because I want to get -3 here and the 3 there to cancel. Okay, so my new matrix then is going to change its row 1. So 1 plus 0 is going to be 0. -4 plus 0 is going to be 0. -2 plus 0 is going to be 0. 0 plus 0 is 0. -3 plus 3 is 0. And then here in the last position, I've got +12 and -5. I have 7. Okay, second row doesn't change right now. Third row doesn't change right now. One more 0. Fourth row is still all zeros. Okay, so I want to keep row reducing this matrix. I need to get a 0 above this pivot here. So remember, when you're going up, you start with the rightmost pivot, and then work to the left. Okay, so I've got -2 above it, so I want 2 copies of row 2, add those to row 1, and replace row 1. Okay, so my new matrix then is replacing row 1, so 1 plus 0 is 0, -4 plus 0 is 0, 2 and -2 makes 0. Sorry, -4 plus 0 is -4. 0 and 0 is going to make 0. Okay, so I got 2 copies. This is 0 and 0 still makes 0. And then the last one, I've got 2 times a -1 is a -2, plus 7 is going to make 5. Row 2 doesn't change. Row 3 doesn't change. Row 4 doesn't change. Okay? Now, I have not written this as an augmented matrix, but you can imagine then that this is augmented with my 0 vector here. Okay? So I can use this to write my solutions. Okay? So I have x1 minus 4x2 plus this is 5x6 equals 0. Second row, now I have x3 minus x6, minus 1, equals 0. Third row, I have x5 minus 4x6 is equal 0. And the last row would be 0 equals 0. So notice I have a few free variables, right? I have no pivot here in the second column. x2 is free, x4 is free, and x6 is free. So I have 3 different free variables. Okay? So when I go to write my equations here, I'm going to take x1, move that to the other side. So I'm going to have x1 is equal to 4x2 minus 5x6. x2 we said is free, so I'm just going to write x2 equals x2. x3 then is equal to x6. x4 we said is free. x5 is equal to 4x6. And x6 we said was free. So we're just going to write x6 there. Okay, so now I can write the solution set for that. Okay, so let me get a clean sheet here to write it, because I can write this in vector form. Okay, so I have my equations. Okay, so let's look at this. I have x2, x4, and x6. So I'm going to have x2 times a vector. I'm going to have x4 times a vector. All right, fighting my camera just a little bit here. There we go. And then x6 times a vector. Okay, so let's look at the coordinates of x2. I've got 4 here first. x2 just has 1 for x2. The rest of them don't have any, so I've got 4 more zeros. x4 now. Well, I have no x4s in that first equation, no x4s in the second equation, no x4s in the third equation. I just have 1 x4 there in the fifth equation, nobody in the fifth or the sixth. So just the one entry there. x6, I start out with -5. And I go 0, 1 in the third equation, right? 1 copy of x6 there. Nobody in the fourth equation. Fifth equation has 4 copies, and the sixth equation has just the 1 copy. All right, so I have my 3 vectors here that are all a part of the solution set. Okay, so when I have 1 vector, that's going to give me a line through the origin. 2 vectors is going to be a plane through the origin, and 3 vectors is going to be a hyperplane through the origin. 3 vectors is a hyperplane. Okay, it is not a space in R3, right? These are still in R6. The vectors are in R6. Okay, but when you put all those combinations together, remember what span means. It's all the combinations of the vectors. So the solution set for this is the span of these 3 vectors, which I'm going to call U, V, and W for expedience. So the span of U, V, and W is the solution set to that vector, to that system. Okay, so if you have a homogeneous system, you either have only the trivial solution, or you have a solution set that is the span of some number of vectors. Could be 1, could be 3, could be 5, depending on how many equations you have and how many dimensions your system has. Okay, so again, please take a look at the homework. See what you need help with, see where I can be of assistance for you. That should wrap up our discussion of 1.5. Our discussion of 1.6 next is going to be over applications. It's a little bit shorter section. I believe the homework assignment just has about 8 problems. I'll have that in front of me right this second. So the 1.6 homework's a little shorter. So if you can get through the 1.5, you're on your way to a good start to the first week. Okay. Again, please contact me if you have questions. Robert.campbell@tamuc.edu. Happy to help or assist you. Visit